For our final chapter in the final unit, Unit 4, we'll look at Chapter 8, which is all about hypothesis testing. In 8.1 and 8.2, which is a focus for this particular video, 8.1 is just understanding what is a hypothesis test, what's the purpose of a hypothesis test, and then in 8.2, we get in a hypothesis test when sigma is known using a z-test. So if you think about in Chapter 7, we talked about confidence interval, and there was a z interval and a t interval. So more or less, the concept is very similar, except we're not constructing a confidence interval. Everything is based on, do we know the standard deviation of the population? And if we do, then we can perform a z-test. If we don't, in 8.3, we'll look at a t-test. In Chapter 8, there are various methods of hypothesis testing. There's 3, but in the time that we have, we're only going to be able to cover 2 of those methods, which is a traditional method talked about in Section 1 of Chapter 8, and then the p-value method, which is talked about in Section 2 of Chapter 8. So for the traditional method, there are 5 main steps that we want to be able to perform in order to do a hypothesis test. And what a hypothesis test is you're basically looking at any type of results you have from a survey or from an experiment. If you want to determine if those results are statistically significant, you perform a hypothesis test. And so we're going to talk about how we can perform the hypothesis test and look at these steps in greater detail. Now, some of the steps you're familiar with. Step 2, finding the critical value, we did that when we did the confidence interval, so that's more or less the same. And then step 3, finding a test value, that's obtaining a z-score from the information provided from the particular problem, and that's more or less what you have been doing for quite a while now. The only thing that's new is how do we state the hypotheses, identify the claim, and then what our decision should be based on, and then a summary, which is just to summarize your findings with a little statement, which more or less kind of like the confidence interval. When you were summarizing that as being a certain % confident, you just, based on your decision you make a little summary. So there's 2 hypotheses that you will have to be able to write, and then we'll talk about how we identify the claim when we actually look at a problem. But the 2 hypotheses would be the null hypothesis, which is identified as H sub O, not ho, but H sub O, so it's like a little subscript of a 0. And the alternative hypothesis is H sub 1, an H with a little 1 subscript. Now, the null hypothesis means there is no difference in what it is you are testing. Essentially, we're doing a hypothesis test only for a mean, because we don't really have time to get into a hypothesis test for a proportion or a variance. So we're only doing a hypothesis test for a mean. And so the null hypothesis represents that there's no difference in the means that we're comparing. Whereas the alternative hypothesis represents that there is a difference in the means, and we want to determine is that difference statistically significant or not. Now, the critical value from the appropriate table, it could be from table E if it were a z-score, or it could be from table F if it were a t-score or a t-value. So that is based on the alpha value, which we talked about from the confidence intervals, right? We spent some time looking at alpha and finding alpha, so we were able to, you have hopefully some comfort level with that. A test value is either a z-score or a t-score, just depends on the problem. And this is the formula that you were introduced a while back when we did in Chapter 6, the central limit theorem, and then again in Chapter 7 when we were doing the confidence intervals. So this formula is still stuck around for quite a while now. And then our decision is mainly based on how we compare that test value to the critical value. And we'll talk about that more in detail when we look at an example problem and actually perform the 5-step hypothesis, this 5-step process. So let's look at first how we can find a critical value, just to re-review that process, but under the guise of hypothesis testing. So it says using table Z, or using the Z table, which is table E, find the critical value or values for each. So we have 3 parts here. And I wanted to kind of touch on the 3 different types of tests we could do. So if alpha is 0.010 or 0.10 for a two-tailed test, and if we remember our discussion from chapter 7, alpha is the area in the tails, right? The total area. So a two-tailed test just means I have a normal distribution, and that 10% or that 0.10 is the area, the total area in the left and the right. So if I split it evenly between the two tails, that means I have 5% in the left, 5% in the right. And so we would need to go to our table and try and find the value closest to 0.05 in the body of the table. So that would be here, 0.0495, which is negative 1.65. And because the distribution is symmetric, that means it's going to be the same value for the left and the right. Now, what we can do is think about if I wanted to confirm that this was the right number. Well, if you have 5% of the area in the right tail, that means this z-score, when I look it up, it should be 0.95, which is the area below that. Because the z-score, when we look at the table, it's always the area to the left. So if I go to 1.65, so 1.601234, this would mean that there is 0.95 or 95% of the area is below this z-score, or to the left of the z-score, which means 5% is above it, which is what we have here. So this would be our 2 critical values. So more or less very similar to what we talked about in chapter 7 with the confidence intervals. We started with a confidence level, and then we talked about how we obtain alpha, 1 minus that number, and then we always divided it by 2 because our confidence interval, these 2 values were containing a percent. So this would be like a 90% confidence interval. But now we're looking at it in a different way, which is the hypothesis testing. So let's look at a critical value for a left-tailed test. So that means that all the area, this 0.01 or 1%, is all focused in the left tail of the test. So 0.01. And if I go to my table, I'll already have the number there, negative 2.33. I want to find the value closest to 0.01. So that's this number, 0.0099, because this is a little further away, negative 2.33. And then for our last little example of the finding a critical value, look at a right-tailed test. So that means this area of 0.04 is all in the right tail. And if I try to go to my table here and look up 0.04, which is this one, it's negative 1.75, which when you look at how we drew it, it's to the right side of the 0. So this should be a positive number. That's because we have to, we're really looking at all the area to the left. So 0.96 is where we want to go. So if I go to 0.96 in the body of the table here, so 0.96, here we go, 0.96. It's the same value, just positive. So 1.7 and 5. So that would be the critical value. So 1.75. So this is just examples of how we will find the critical value when we look at doing the hypothesis testing here in just a moment. So let's go through and run through the steps and see how we can talk about those 5 steps I talked about in the beginning, and then kind of run through what the results tell us about this particular situation. So this is about Facebook friends. So many people believe that the average number of Facebook friends is 338. The population standard deviation is 43.2. A random sample of 50 high school students in a particular county revealed that the average number of Facebook friends was 350. At alpha equals 0.05, is there sufficient evidence to conclude that the mean number of friends is greater than 338? So immediately we're given a bunch of values. I read it once through. We go through, read it again. So at first we're being told that people believe that the average number of Facebook friends is 338. So that's our population average, 338. And then we can continue to read the population standard deviation is 43.2. So we're going to need that information as well. And then we have a sample of 50. And the average number from that sample was 350. And our alpha is 0.05. So these are 5 components or 5 values that we want to be able to identify from this particular problem. And then we'll talk about the 5-step hypothesis. So for step number 1, we want to identify our 2 hypotheses. We want to identify what is the null hypothesis and what is the alternative hypothesis. The null hypothesis represents that there is no difference in the averages. So the population average that people believe represents the number of Facebook friends is 338. However, a sample was collected and we got 350. So the null hypothesis just indicates there really is no difference in the mean. So it's assumed that the true average is 338. The alternative hypothesis represents that there is a difference, and then that's what we're looking at to see, is that difference statistically significant or not? In this case, says, is there sufficient evidence to conclude that the mean number of friends is greater than 338? So for our alternative hypothesis, our H sub 1, it's that the true average is actually greater than 338 based on the sample that we collected. So this is our first step in the hypothesis process. And then we identify our claim. Generally, in each problem, the alternative hypothesis is your claim unless stated otherwise. So in the problem, it doesn't say anywhere the claim is this. So we go with our claim being the alternative hypothesis. That's our first step. Second step is what is our critical value? And that critical value is based on alpha. Now, the type of test is a right-tailed test, and that is always based on the alternative hypothesis. Right-tailed because it says greater than. So we look at alpha is the area in the tail. So we shade off an area of 0.05, and we want to figure out, what is that z-score? What is the z-score that represents this particular area? Which means we go back to our table and we need to look at 0.95 and figure out what that is, which we did that earlier, but I'll go ahead and check it anyway. So if I go to my table E and look for 0.95 in the body of the table here, here is 0.9505, so 1.6 and then 5. And we need this value along with step 3, which is the test value. The test value is based on the actual data that has been collected. So we have to find the z-score now based on that information. So we utilize our z-score formula. And this is a formula back from chapter 6 when we first introduced the normal distribution, and then utilized again in chapter 7. So we substitute in those values and we figure out what is the z-score, 1.96. And what we need to do is compare that value to the critical value. Now, the region that's been shaded in here, the green area, is known as the critical region, right? That's the critical region, or I like to call it the rejection region. If our test value is inside this critical region, or if our test value is inside the rejection region, then our decision is to reject the null hypothesis. So in this case, we would reject the null hypothesis since this particular test value is inside the critical region. And by rejecting the null hypothesis, so this question, is there sufficient evidence to conclude that the mean number of friends is greater than 338? Well, we could say yes to that. There is sufficient evidence to conclude that because we are rejecting the null hypothesis that says there is no difference. If we reject this notion, that means there is a difference, and we're looking at the alternative hypothesis now. So now we do our summary, which is the 5th step. Step number 5 is a summary. So there is convincing evidence to support the claim that the average number or the mean number of Facebook friends is greater than 338. And so those are the five steps. A little tedious, hopefully not too difficult, just probably a little more tedious than anything. But when I kind of run back through them, step number 2 is more or less review, because we found critical values before back in chapter 7. Step number 3, also more or less review. You have been finding a z-score using this formula since chapter 6 when we did the central limit theorem, 6.3. And then the only thing that's really new in this process is how we state the hypotheses, how we make our decision, and then the summary. So those are the 3 things that are more or less new for us in chapter 8. So let's look at another example. So in this example, we have some raw data. It says heights of 1-year-olds. The average 1-year-old of both genders is 29 inches tall. So that represents my population average, right? That's the average of all 1-year-olds, male or female, boy or girl, 29 inches tall. And then a random sample of 30 1-year-olds in a large daycare franchise resulted in the following heights. So our random sample of 30, well, that's our sample size, n equals 30. And these are the following heights it's referring to. At the alpha equals 0.05, can it be concluded that the average height differs from 29 inches? So we have our standard deviation here, 2.6. Now, what we have to find is the mean, right? Remember, we have to identify 5 values, and those 5 values are the population average, the sample size, the standard deviation, the sample mean, and also alpha. We have alpha, so we need to find this. Just add those up and divide by 30. So we add those up, divide by 30, we get 29.45, and then we can talk about our 5 steps. So the first step, what is my hypotheses? Our hypotheses, the null hypothesis, is always going to be that the population average is equal to something stated in the problem. So there really is no difference in the averages when we look at the sample statistic versus the population parameter. Since there is no difference, we look at our null hypothesis being that the average is equal to 29. Versus the alternative hypothesis, we have the average is not equal to 29, and we know it's not equal because of the word differs. Differs could mean that, in this particular sample, the average was a little higher than 29. If they took another sample of 31-year-olds, it could be less than 29. So they're really not quite sure if the true average is more than 29 or if it's less than 29. So we use the word differs in this case. Step number 2, critical value. The alpha value is 0.05, but same as the previous problem, but now we have a two-tailed test because it's not equal to, which means that area, that 0.05, is divided into both of those left and right tail. So we have an area of 0.025 and then 0.025 on the right side, and we go to our table E and we look for the value closest to 0.025. So 0.025, here we go. So negative 1.96. And since the distribution is symmetric, it's the same on both sides. And then step 3, we find our test value, which is a z-score. So we substitute in our values and we end up getting a z-score of 0.94. Now, if we look at I'm going to go back, that was too quick. If we look at our distribution here, 0.94 is on the outside of the rejection region or the critical region. So because that this number is on the outside of the rejection region, we look at our step number 3 or our step number 4, what our decision is. Our decision is to not is to not reject the null hypothesis. So since the z-score of 0.94 is not in the critical region, we do not reject the null hypothesis. And that leads us to our decision because there's really not a statistical significance since the z-score does not fall within that critical region or that rejection region. So we look at our summary can it be concluded that the average height differs from 29 inches? Well, there is no convincing evidence, or there is not convincing evidence to support the claim that the average height of 1-year-olds is different than or from 29 inches. So for this question, this is the summary that we need to write, but then to answer the question, can it be concluded? No, it cannot be concluded. So that's these two examples represent the 5-step hypothesis test process for the traditional method. The other method is the p-value method. And when we look at the p-value method, it still has 5 steps, and 2 of the steps are kind of swapped in comparison to the traditional method. So step number 1 is the same as the traditional method. State your hypotheses. You still have an H0, which is equal to some number stated in the problem, and you have your alternative, which is one of those 3 values. Is either the average is less than, the average is more than, or the average is not equal to, based on the wording in the problem. So that's no change. The test value now comes second, so there is no finding of a critical value here, because we now look at a p-value, which is a probability value. But before we can find the p-value, we need to find the test value, which is the same calculation as before, right? That same formula. So what a p-value represents, the p-value is the evidence against the null hypothesis. If I draw a distribution here, and I kind of say, let's say that we have a left tilt test because the symbol was less than indicated in the problem, and this was the z-score calculated from my test value, then the area to the left of that z-score would be considered the p-value. It's just a probability. And we first learned in the previous unit, unit 3, about how we can use a normal distribution as a probability distribution. So the smaller the p-value is, the stronger the evidence that you should reject the null hypothesis. And that's what this is telling us here. Make our decision based on the p-value. If the p-value is less than alpha, because now we're comparing a probability value to another probability value, because alpha is more or less, it's the area in the tail, but it's also considered a probability value. So if this probability value is less than or equal to this probability value, then we reject the null hypothesis. If the probability value is greater than this probability value, we do not reject the null hypothesis. And then we summarize our results. So we'll look at some examples of that. Farm sizes. So the average farm size in the United States is 444 acres. That is our population average. A random sample of 40 farms in Oregon indicated a mean size of 430 acres. So we know we have a random sample of 40. Of those random sample, they have an average of 430 acres. And then the population standard deviation is 52 acres. And then we have our alpha value. So we have our 5 values that we need to identify. Step 1, identify our hypotheses. Our null hypothesis is that the average farm size is no different than the national average farm size, 444 acres. Our alternative hypothesis says, can it be concluded that the average farm in Oregon is less than the national mean? Well, we use the less than symbol in this case, less than 444. And this is our claim because it's not being stated otherwise in the problem. For step number 2, we find our test value. So we calculate the z-score, utilizing the numbers provided. And then step number 3 is where we talk about p-value. So this is different than the previous 2 examples. The p-value is based on this z-score of negative 1.7. So I know this is a left-tailed test because of the less than symbol. And also my z-score more or less confirms that because it is a negative value. So I mark that off, shade in the area, and then I have to look at table E to figure out what is this p-value? What is the probability of this? What does this area represent as far as a portion or a probability from table E? So we go to our table and look up negative 1.7. So 0.0446 would be the area to the left of that z-score, which is also the probability. So my p-value is 0.446, and then we look at our decision. So since the p-value of 0.446 is less than our alpha value of 0.05, we must reject the null hypothesis, right? Because this is considered small relative to this number, we have to reject this. We reject this value here. Since we are rejecting that value, we look at, can it be concluded that the average farmer in Oregon is less than the national mean? Yes, it can be, because we're rejecting this, that there's no difference. So when we do our summary, there is convincing evidence to conclude or to support the claim that the average farmer in Oregon is less than the national mean, which is 444 acres. All right, and we'll do one more example with some raw data again, and also the p-value method. So now look at speeding tickets. A motorist claims that the Southborough Police issue an average of 60 speeding tickets per day. These data show the number of speeding tickets issued each day for a randomly selected period of 30 days. Assume sigma 13.42. Is there enough evidence to reject the motorist's claim at alpha equals 0.05? Use the p-value method. So again, we start off with finding the important information. So our population average is 60. They give us sigma 13.42. They give us our sample size, which is 30. Here, we can also count that information from the problem. And then our sample mean is just adding these up and dividing by 30, which we get 59.93. And alpha, we have the same alpha value. Generally, the alpha values will stay around the same. It could be 0.01, it could be a different number, but it generally fluctuates between 0.01 and 0.05. And we look at our 5 steps. So first step, my hypothesis, my null hypothesis. Well, there really is no difference in the average number of speeding tickets. So we look at the mean number of speeding tickets being 60 versus the mean number of speeding tickets being not equal to 60. Now the problem doesn't mention anything about the number of tickets increasing or decreasing, so we go with not equal to because of that. We can't find a definitive word that tells us, do we think that the true average is less than 60, or do we think that the true average is greater than 60? And then we find our test value. This is our claim now because of what it says in the problem. A motorist claims that the Southborough Police issue an average of 60 speeding tickets per day. So now this is our claim because it's being stated in the problem. The other 3 examples, it was never stated, so we use the alternative as a claim. But now we look at our z-score, and we get negative 0.03, very, very small z-score. Well, I guess not very, very small, very close to 0. So then step number 4 is p-value. Because this is a two-tailed test, right, not equal to, that means a two-tailed test. That means we look at not only this negative z-score value, we look at the positive z-score value as well. So we have negative 0.03 and we have positive 0.03. And we do this especially for the sample data. So this is just one sample of a period of 30 days, a randomly selected 30 days. If by chance whoever is conducting this survey or experiment, if they are collecting another random 30 days, maybe the average they get will be greater than 60. And if they repeat this process many, many times, you could get averages, you'll get averages below 60, above 60, below and above, until you decide to stop collecting data. So with a two-tailed test, you look at both ends of the spectrum, values that are below the mean and values that are above the mean, because you're not really sure what results you'll get. So for our probability value, we have the area in both tails that we have to find. So now our p-value would be this area or this probability plus this probability, because you could either be below the mean or you could be above the mean. And so when we go to our table, we want to find an area of 0.03, not an area, we want to find a z-score of negative 0.03. So 0.0 negative 1, 2, 3, 0.488. And since the distribution is symmetric, that means it's the same area in both sides. So for a two-tailed test using the p-value method, we have to double that area. So this would be the probability from this particular result, 0.976. And then we look at our decision, that p-value is quite large. Since it's much larger than our alpha value, we look at not rejecting the null hypothesis. So again, when we talk about statistical significance, we want a smaller p-value. We want a relatively small p-value in order to reject the null hypothesis. Since this value is pretty large, we can't reject the null hypothesis, because the p-value is the probability of obtaining our results at least or extreme as the results that are observed. So it's the likeliness that we are going to continue to get these observed results here in the sample collected data. So there's a 97% chance that we're going to continue to see these kind of results, which are more or less that value is not much different than the 60, right? It's relatively close, right? Because the z-score is so close to 0, and a z-score of 0 represents 60%. So when the p-value is large, it just indicates that our observed information is pretty much the same as what we expected, the 60, or what was being claimed. If the p-value is small, very small, that means the z-score is a very small number, further away from the average, further away from the average we expect, or further away from that average of 60, and so it's not likely to happen by chance, which means it is statistically significant. So that's when we end up rejecting the null hypothesis. So in this case, because we have that large p-value, we do not reject it, and then our summary this time, we can say there is convincing evidence to support the claim because our claim was the null hypothesis. So there is convincing evidence to support the claim that the Southborough Police issue an average of 60 speeding tickets. And then we look at the question here, is there enough evidence to reject the motorist's claim at alpha equals this? No, there's not enough evidence, because here we're supporting that claim based on the p-value method, based on the results based on the results from the survey that we conducted, or the test that we conducted.